Now, we have observed that the distribution of the Wiener process at any time instant has a Gaussian distribution. Now, we will generalize this and we will investigate the general uh, class of Gaussian random processes. Okay, and we start with the definition. A random process x of t is a Gaussian process if the samples x of t1, x of t2, etc., up to x of tk are jointly Gaussian for any choice of these t values and any choice of the number of samples. Okay, so that means if you have a random process, if you observe it at a bunch of points, regardless of um, how many observations you make, and regardless of where you make the observations, if the joint distribution turns out to be jointly Gaussian, then we say that this process is a Gaussian process. It can be a continuous time or discrete time, but obviously it's continuous valued because it's Gaussian. The great thing about Gaussian stuff is, as you know, if you know the mean and if you know the covariance matrix in the general case, uh, you can have the distribution. You can characterize it in any way you like. So that means for this random process again, if you have the mean vector for your observations in time t1 through tk, and if you have your covariance matrix, that is sufficient to entirely characterize this random process. Okay, that means the mean mu x of t and autocovariance t1, t2 completely specifies the Gaussian random process. Be careful here, but look, the mean may depend on t, and the autocovariance function may depend on t1 and t2 separately. Okay, a random process being Gaussian does not guarantee it to be stationary. Okay, this is quite important. Sometimes people assume since my random process is Gaussian, it should also be stationary. That is not the case. Be careful about this. The mean can depend on time. The autocovariance can depend on T1, T2 separately. So in general, a random process being Gaussian does not mean it has to be stationary. And as I said, Wiener process is an example to Gaussian processes because wherever you sample it, it is a Gaussian distribution. And how many samples you take, those will have jointly Gaussian distributions. It's not that difficult to show, but I'm not going to do that. Now, let's assume we have a White-Stein stationary Gaussian process. As I said, being Gaussian does not guarantee any sort of stationarity. But assume that now random process x of t is Gaussian and also White-Stein stationary. And of course, in this case, since it is White-Stein stationary, the mean will be independent of time, and the autocovariance will only depend on the separation of time instants. In this case, of course, you can write the joint PDF for any number of samples based on this joint Gaussian PDF, as we very well know by now. And here, the covariance matrix, right? The covariance matrix is the covariance at T1 minus T1, T2 minus T1, T3 minus T1, etc., up to Tk minus T1. And in the second row, I have covariance at autocovariance at T2 minus T1, then T2 minus T2, then T3 minus T2, T4 minus T2, etc. Okay, so this is the covariance matrix. But you see, if I shift every time sample by tau, okay, so T1 becomes T1 plus tau, T2 becomes T2 plus tau, etc. Tk becomes Tk plus tau. Well, the mean is not affected, obviously, because it is independent of time. But also, when you look at the covariance matrix, the autocovariance, this was T1 minus T1. This is T1 plus tau minus T1 plus tau. Still 0. And the second term, it will be T2 plus tau minus T1 plus tau. It will still be T2 minus T1. The third one, it will be T3 plus tau minus T1 plus tau. It will still be equal to T3 minus T1. So this matrix will be exactly the same with this matrix, which means this distribution will not change because this matrix will be the same. Mu, as we have established, is the same, is independent of time. This mu is still the same, and this matrix stays the same with respect to time shift. And therefore, when you have a White-Sands stationary Gaussian random process, if you shift every observation by the same amount tau, the joint PDF does not change. What does that mean? This is by definition stationarity in the strict sense, okay? Because this is true for any value of k, any value of t1, t2 up to tk, and any value of tau, clearly. Therefore, we see that if you have a White-Sands stationary Gaussian process, then it is also stationary in the strict sense, okay? This is an extremely useful property of Gaussian random process. In general, I have said that White-Sands stationarity does not imply stationarity in the strict sense, obviously. It's the other way around. If you have strict sense stationarity, you have White-Sands stationarity. But it's not like you have a White-Sands stationary process, which means it's strict sense stationary. No. But only in the case of Gaussian process, you have when a White-Sands stationary, when a Gaussian process is White-Sands stationary, it is also guaranteed to be strict sense stationary. So this is a little bit like independence implying uncorrelatedness, but not the other way around. But when it comes to Gaussian random vectors, uncorrelatedness also implies independence. It's a little bit similar to that. So in general, White-Sands stationarity does not imply strict sense stationarity. It's the other way around, but only if you have a Gaussian process which is White-Sands stationary, then you also know that it's also strict sense stationary.